What is a data structure? A data structure is a collection of values. Algorithms are the steps or processes we put into place to manipulate these collection of values. It's what allows us to write programs. A person who knows how data structures and algorithms work and how to use them can write programs, great programs. The beauty is that these are timeless. No matter what programming language you use, whether you prefer one library over the other, whether you write code in Angular or React in the front-end development world, or you're a game developer, underneath it all, it's all data structures and algorithms. If you understand these, then you can really easily adapt and tackle all sorts of technical problems. It is why companies like Facebook, Amazon, Netflix, Google ask questions specific to data structures and algorithms. Because although it may be important to know the latest and greatest JavaScript syntax, or maybe the latest and greatest library, those things change. If you know the fundamentals though, then they can throw you any problem, any situation, and you're able to make the right decision. This knowledge is extremely valuable. The longer you are in the field, the more and more you realize that you need these fundamental principles of data structures and algorithms in order to be a great developer or engineer. So let's get started with that. Over the next few sections, we have a long way to go to get familiar with data structures and algorithms so we can write great programs. Let's get started. Welcome back. What is a data structure? A data structure is a collection of values. The values can have relationships among them and they can have functions applied to them. Each one is different in what it can do and what it is best used for. Most important thing to take away is that each data structure is good and is specialized for its own thing. All right, Andre, you just said a bunch of words and I don't really understand. Well, let's show you a couple of images to simplify this. You see, you can think of data structures as any sort of compartment or container. A data structure is simply a file cabinet of different types. You have a backpack, a place where you put maybe your school books. You have drawers where you put your clothes, a fridge where you put your food, a folder for your files, and a packing box maybe for your toys. Each one of these containers are useful for its own thing. For example, I'm not going to put my food in a drawer over here because that yogurt is going to go bad here. Likewise, I'm not going to put all my papers and files in my backpack or perhaps a toy box because it's just going to get crumpled up. Each one of these containers are specific for its own thing. And that's what data structure really is. It's a way for us to organize data so that we can go into the backpack and retrieve that data really easily. We can go into the fridge and grab that popsicle or ice cream really fast. We can put things in data structures and we can take things from data structures. And that's all it really is. And there are a ton of data structures. Just like in our real life, how we have all these containers, all these places to put things in programming, we have a ton of them. If we go to Wikipedia, for example, well, if we scroll through here, we see a ton of data structures. And this is going to look overwhelming, but don't worry. Most of these, well, I've never encountered myself, and they're very, very specific. You probably only have about 5 or 6 data structures that are really, really important that we're going to go over. And you may have even heard of Bitcoin and how it uses blockchain technology, this magical word. Well, blockchain at the end of the day is simply a data structure, a way to hold information. So in our programming world, data structures, we can store things like numbers, strings, Boolean types, just like we saw when we coded in JavaScript with arrays and objects. Arrays and objects in JavaScript are each a form of a data structure that allows us to store information. You see, as humans, this is what we do on Earth, right? We take the chaos and the disorder and make order out of it. At least we try to. We organize our farms to produce food. We package the food and we deliver them to the grocery stores and organize them in the grocery store so that humans can grab those and can then purchase these groceries and give money to put in a compartment and a bank. That's what programs are. We're modeling real life scenarios. And The more advanced a developer you become, the more time you'll start thinking and spending time talking about data structures. This is why interviewers love to talk about data structures. Now, as I always like to mention, there are always trade-offs. Every programming question has a trade-off. Remember our 3 pillars of readability, memory, and speed when we talked about what code is best? Well, we have the same thing with data structures. One is better than the other in some aspects and the other better than the other. That's why they exist, each one for its own specific case. And there are 2 parts to understanding data structures. One is how to actually build one. How can we build with code some of these data structures? And 2 is how to use them, how to use these data structures. We're going to do both of these in this course. But the second point is the most important, right? Because data structures are usually just tools. And most of the time, they're already pre-built for us. The most important part is how to use them, when to use one over the other. And we kind of saw a little bit of that in the previous section when we talked about how to solve problems, where we used an object versus an array to make our code more efficient. The goal in this course is to understand data structures so that you can pick the right data structure for your problem. Based on different scenarios, data needs to be stored in a specific format. We have a handful of data structures that cover our need to store data in different formats. So let's get a little bit deeper into this topic. In order to truly understand the value of data structures, we have to go deep down into the way a computer works at the fundamental level. In order for a computer to run code, it needs to keep track of things like variables, like numbers, strings, array. These variables are stored in what we call random access memory, or RAM for short. That's how programs run. We remember this from Space Complexity video, right? On top of that, we also have storage, where we store things like our video files, music files, documents. And the storage can be a disk drive, a flash drive, or a solid state drive. Data on storage is permanent, or what we call persistent. So when you turn off your laptop or computer, it's still going to be there when you turn it back on. In RAM, you lose the memory when the computer turns off. So why wouldn't we just always use storage so we don't lose any data? Well, the problem is that persistent storage is slow. Because you see, a computer is run by its CPU. You can think of the CPU as the little worker that does all the calculations that we need. It does the actual work inside our computer. And this CPU needs access to the RAM and the storage. But it can access the RAM and the information in the RAM a lot faster. But let me give you an example as if we're using Google. When we run Google Chrome, for example, a browser, that Google Chrome browser has a piece of code. Now here I've simplified it, and we just have a variable a equals 1. We're just assigning this variable 1. But we can imagine how we have hundreds, thousands of lines of code of Google Chrome. Now, in order for our computer to run Google Chrome, we run the CPU for it to do so. Now, when a variable is declared in, let's say, a script to run Google Chrome, it's going to hold that in memory, in our random access memory. But once we turn off or close Google Chrome, we want to be able to reopen it, right? Well, that's what we do when we save an application on our computer. We save it to storage so that next time we open up Google Chrome, the CPU is going to grab the program from the storage so that it can use it again. And for Google Chrome to run fast and run smaller scripts, it's going to keep that information in random access memory. We can see this on our computers as well. If I go to About This Mac, my computer, we can see here that we have the processor, which is my CPU. We have my memory, which is my RAM. And if I go to storage, this is my flash storage, my persistent storage on my computer. So you can think of RAM in the computer as a massive storage area, kind of like a data structure, right? Well, this massive storage area has shelves that are numbered. We call these addresses. And it's a really, really big shelf that holds a lot of information. And it allows us to run programs on our computer. Now, Each of these shelves holds what we call 8 bits, or numbers. If you see here, 1, 2, 3, 4, 5, 6, 7, 8. Each one of these numbers is a bit. And a bit is a tiny electrical switch that can be turned on or off. But instead of calling it on or off, we call it 1 or 0. And 8 bits is called a byte. Each shelf has 1 byte of storage. And the CPU is connected to something called a memory controller. And a memory controller does the actual reading of this memory as well as writing this memory. Because sometimes this shelf might be blank and doesn't have anything. Now, this direct connection to the CPU is important because the CPU asks the RAM, hey, what's in shelf number 0? And the memory controller actually has connections individually to all of these shelves. Again, that's really important because it means that we can access the 0 shelf and immediately access the 7 shelf or 10,781 shelf without having to climb down or step down. That's what the name random access memory means. We can access memory really fast because we have these connections any shelf we want. We just need to know which shelf we're looking for. We can access the bits at any random address in memory right away. Even though this memory controller can jump between far apart memory addresses really fast, programs tend to access memory that is nearby. The closer the information is to the CPU and the less it has to travel, the faster a program can run. So computers are actually tuned to get extra speed boosts when reading memory addresses that are close to each other. For a computer to access 0 and 1 is a lot faster than a computer for it to access 0 and 1,000, because these are a lot closer together. And to further optimize this, our computers also have what we call a CPU cache, where the CPU has a tiny, tiny memory where it stores a copy of stuff that is really, really recent. And this is called a cache. A common one that you might hear is something called LRU cache. So again, if we use Google Chrome as an example, we turn on Google Chrome with, let's say we have the application downloaded on our storage, the CPU loads it up, and because we've visited hackernews.com, it's going to load up the information for that Hacker News and put it into memory, or maybe even cache, if it can hold it. So, why is this important for data structures? Well, data structures are, remember, ways for us to store information. For example, if we want to store variable a equals 1, well, in our modern computers, usually we represent integers, that is the number 1, in 32 bits. That is this block size of RAM. And by the way, this is now can be 64 bits with more and more recent upgrades. But this way, we can store the number 1 within this blocks of 32 bits. Why 32 bits? Because 8 bits, which is 1 byte, times 1, 2, 3, 4. So 8 times 4 is 32 bits. We can store 32 bits of information. And this bit of 1, you can see here, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 1 is stored now in memory 0, 1, 2, 3, or the address 0, 1, 2, 3. If we have another variable b equals to 7, we would store it in the next block over here in our RAM. In doing this, you can now think about how systems that are 8-bit can hold 255 bits of information. Things that are 16-bit, well, they can hold a lot more information. And now we have systems that are 32 bits. You can see here that we can hold a ton of information. And then if we had 64 bits, that is, instead of having 4 little shelves over here, we have 8 shelves. Shelves times 8 bits. Well, that's a lot of information that we can store. And the bigger this is, the more diverse that information is. If we had an 8-bit system, well, the number 256, we can't really store that. That's really hard to do. And I can demonstrate this to you with JavaScript. You see, there's something called integer overflow. Now, JavaScript technically doesn't have integers. It only has what we call a 64-bit floats. But the idea is that a computer can only store a certain number of information. So using this syntax in JavaScript, we have math.pow, which is a function that returns the base to the exponent power. That is, the first parameter is the base to the power of the second parameter. So we can create really large numbers like math.pow, so 5 to the power of 100. If I run this, we see the number over here. If I increase this to, let's say, 6, again, another large number. Now, what if I keep going and change this to 6 to the power of 1,000? We get infinity. What is that? Well, as the number becomes too large to store in our RAM, then we need to represent this number that we cannot store into something that is tangible. In JavaScript's case, it is infinity. We can only store this much information, and no matter how big I make this, any number above a certain threshold is going to just say infinity. How cool is that? Now let's go back to the slides. I showed you all of this because other data types other than numbers work the same way. Each data type has a number of bits associated with it, and that needs to get stored in the system. And the system allocates that storage, and then the CPU reads from that storage. Now, I'll leave a link for you after this video so that you can get more information if you want. We don't want to get too deep in this. But a data structure is this. A data structure is an arrangement of data. You can define the way you interact with this data and how it is arranged in RAM. So some data structures in RAM are organized right next to each other. Some are organized apart from each other. And they have different pros and cons on access and write. Our goal is to minimize the operation that we need to do for the CPU to get the information, for the CPU to write information. And that is why data structures are so powerful. We're thinking about the low level. And I don't know about you, but this to me, when I learned about this, was really, really exciting. Because we have a way now to think how data structures actually affect the process of our computers, and how we can use what we know about computers now to write great code. I'll see you in the next video. Bye-bye. Welcome back. There are quite a few data structures that you may be asked in an interview, and we saw how many of them there are on that Wikipedia page. But luckily for you, the list isn't actually that intimidating. All you need to learn are these ones over here. These are used, I would say, 90% of the time. And this is what we're going to talk about in our course. Now, there may be specific ones within these groups, and each one of them has trade-offs. But as long as you learn these and you learn when and why you should use them, then you're going to be miles ahead of most people. It's going to be a lot of fun. Now, before we get going, I want to note one last thing. You see, each language has their own data types, or built-in data types. JavaScript, for example, has numbers, strings, has booleans, which are true, false, and then some strange ones like undefined. And each language has data structures to organize these data types. So for example, in JavaScript, we have arrays and objects that we use. And they are data types. It allows us to structure and organize information such as our primitive data types, or even hold more complex ones like having an array that contains multiple objects. And we're going to talk about this in more detail, but I want to show you that we do have different languages that have different access to some data structures. You can see over here some of the other languages that we can use in this course and whether they have them available. We see that Java has arrays, has linked lists, stacks. We have priority queues, and many other types. Now, does that mean that if we're using JavaScript, we can only use arrays and objects? Well, no, not really. Although these languages come with data structures built in, we can also build our own. And most languages have enough data structures and data types for us to build and create our own data structures. So if JavaScript doesn't have stacks, well, we can build one. Now, to finish this section and finally dive into our first data structure, I wanted to just remind you that we have a little map over here of what we need to know for the coding interview. Now, in this map, I have a little present emoji next to each one of the data structures that we're going to talk about. As you can see, there aren't that many of them, and many of them are quite related or are children of the other. But use this as a reference for you to just draw a map of how things are connected and what the data structures are that we're going to talk about. But let's get our hands dirty with our first data structure. I'll see you in the next one. Bye-bye. What are the various operations that can be performed on different data structures? Because as we learned in our previous lectures, data structures are simply ways to organize our data on our computers. And the data structures we'll see throughout this course are simply variations of how we store this data on our computers, this information. And each data structure has their trade-offs. Some are good at certain operations, others are good at other operations. One type of action that we're going to perform with data structures, is insertion. Add a new data item in a given collection of items, such as us adding the Apple item in memory here. Another one, deletion. We want to sometimes delete data, such as remove Mango from our list. Another type of action might be traversal. And we're going to see this a lot. Traversal simply means access each data item exactly once so that it can be processed. Another useful one is searching. We want to find out the location of the data item if it exists in a given collection. And then we also have things like sorting. That is, having data that is sorted, kind of like it is on the left-hand side over here, versus the right-hand side where there's not much sorting going on, at least from what we can see. And obviously, the main one, and probably the most important, is access. How do we access this data that we have on our computer? Now, each data structure that we're going to go through in this course will have different pros and cons for each one of these. And if we take a look at our Big O cheat sheet, we're very familiar with this diagram over here, or this graph. And if we scroll down, we have all these data structures that it lists. And don't get too overwhelmed. We're going to go over most of these data structures, and you see that half of them are mainly trees and variation of trees. And within here, we see that each one of them has access, search, insertion, deletion, average, and worst case. And because we understand Big O, we can see that, all right, we're seeing which one's good for what and what is bad for what. And as we go through our data structures, we're going to go over these pros and cons so that you build the foundation to be able to decide which data structure should I use on your next problem. We're going to get started with our very first data structure in the next lesson. I'll see you in that one. Bye-bye.